So today is a big day for our random walk simulation. Today's the day we move into 2 dimensions. Previously, our random walk was governed by a coin toss that determined whether our random walker would move a step upward or a step downward. Now we've got 4 possible steps to take. We can take a step to the right, it's a vector 1, 0, 0. We can take a step to the upward direction, that's 0, 1, 0. We can take a step to the left, negative 1, 0, 0, or we can take a step downward, 0, negative 1, 0. So instead of having our previous function up or down, we're now calling that function direction. And basically we've got a 25% chance of moving in any of those directions. So each loop in our random walkers are going to take a step in one of these 4 cardinal directions. They're not going to be moving diagonally. In order to help us visualize this motion, I'm creating a lattice of spheres. So these just represent the points that they can go to. So they're just positioned along in the x and y direction in steps of dx, the same step size as the random walkers. Here we've got our random walkers, Kramer and Josh, just like we had back in our one-dimensional random walk. Actually, these are the graphs for their position. Here we have the actual random walkers, excuse me. We're going to definitely have them make a trail so that we can see the pattern that they leave behind. And then here we haven't changed too much about the loop. Basically, instead of just updating the y coordinate of the position, we're now updating the entire position vector for Kramer and Josh with this randomized direction, up, down, left, or right. And I've done something a little bit different with the graph here. We're going to be graphing the magnitude of their position vector so that we get their distance from the origin, from their starting point. All right, let's hit Control 2 to run this thing. So here we've got our lattice of points. Again, they're restricted to move to, this spacing of points. And of course, they move in different directions. And so their trajectories, it's basically, kind of random segments along this lattice. They both started back here at 0, 0. Of course, they can go off of this lattice. Just imagine that this grid of dots, extends all the way across the screen. And so, yeah, you get these pretty neat patterns. Again, this would be neat for making a coloring book for your kids. I don't know how exciting it is to color in squares, but, it teaches them, to color in patterns and things like that. You could use this as an example to teach, like the 4-color theorem for coloring in maps, that you only need 4 unique colors to completely color every opening and have no 2 of the same colors touching. And it proceeds pretty much like you would expect a one-dimensional random walk to proceed. In fact, another way you can think of a 2-dimensional random walk is 2 one-dimensional random walks kind of superimposed. So if I think about, Josh is the green one, right? Yeah, Josh is green. So if I think about Josh here, Josh is really making a random walk in the y direction, and he's making a random walk in the x direction. The only difference is that in each of those directions, he's going to have to take a pause to then move in the other direction. So instead of having, jagged peaks like you would have last time, you would have jagged and then a plateau, and then jagged and then a plateau. Same thing for Kramer down here. He's just got a different set of, I guess we're not flipping coins anymore. I guess we're rolling a d4, a 4-sided die here. Let's take a look at the vector magnitude that we're graphing here. So again, this is the magnitude of their positions. This is how far away they are from the origin. So we've had 1,100 steps now. You see, it looks pretty similar to the type of random walk graph we had before, because they're always going to be taking a step of 1. It's just now we're adding in a square root and a squaring to get the Pythagorean theorem. So it's not quite the same step size each time, but it's very similar in shape, getting, some nice, mountain ranges again. One of the things you notice is that after here, they drift off and they haven't gotten back to the origin yet. So the origin is the only point that's going to have a magnitude of 0. Josh got pretty close at this point, got pretty close back to the origin, but then turned around. Of course, once they leave the origin, there's nothing really special about that point. It's just in their history is the point that they began at. But that is something we're going to test in the next video, is how likely is it for a 2D random walker to eventually return back to the origin. And there's actually a proof in mathematics that says that a random walker in 2 dimensions will almost surely return to the origin. And almost surely there is a technical term meaning it's basically a 100% probability, although you can come up with cases where it won't happen. It's almost inevitable. And so we call a 2-dimensional random walk a recurrent random walk, whereas in 3 dimensions it's called a transient walk because you're not guaranteed for a random walker to end up back at the origin. So in the next video, we're going to take a look at testing that claim by the mathematicians that a 2D random walker will almost surely return to the origin. And then in the video after that, we're going to extend this animation here into 3D. So if you think this looks pretty cool, wait until you see it in 3D. So thank you so much for watching. I will see you next time. Bye-bye.